In question 4a, we are told that 1 plus I is a root of a complex number equation. We must use this to solve for the unknown value of p. To start, we sub in z equals I plus 1 into the equation. Then we can rewrite 1 plus I squared as 1 plus I times 1 plus I. Now we can expand our two pairs of brackets. Next, we combine like terms. Then we can use the fact that I squared is equal to minus 1 and simplify 4 plus 1 to 5. As the final step, we subtract 5 plus 3i from both sides. Part B involves an application of de Moivre's theorem. This requires our numbers to be written in polar form, so the first step is to use our calculator to convert the given complex number into polar form. Our equation involves w squared. To find w, we should square root both sides of the equation. We have to be careful to remember to write in a plus minus sign here. This is necessary because positive and negative versions of the same number both square to give you the same result. Now we can apply de Moivre's theorem with r equal to 2, theta equal to 120, and n equal to 1/2. We can simplify, use our calculator, and then multiply in the root 2. To obtain our final answers, we split the plus minus sign into two separate cases. In part C, the complex number u is equal to a plus bi is plotted on an Argand diagram. In part 1, we must calculate iu and iu conjugate. Since u is equal to a plus bi, iu can be written as I times a plus bi. This expands to ai plus bi squared, and since I squared is equal to minus 1, this can be simplified to ai minus b. Writing the real component first, this becomes minus b plus a times I. To find the conjugate of this number, all we have to do is change the sign of the imaginary component, so the plus ai becomes minus ai. In part 2, we plot these numbers on the Argand diagram. In part 3, we need to send u to iu conjugate. There's two steps here. First, we multiply by I, which corresponds to a rotation of 90 degrees anti-clockwise. Then we take a conjugate, and this corresponds to reflecting in the horizontal real axis.